Earlier we saw that paired designs are useful because they allow us to account for unwanted variability in the response. In this video we're going to talk about a randomized block design, which works in a similar way, but the benefit is that it allows us to compare more than two treatments. So in this example we're looking at a study to compare the effect of caffeine with theobromine, I think is how you say it, which is a chemical naturally found in chocolate, similar to caffeine in terms of molecular structure. And we want to measure the effects of these chemicals. So researchers trained subjects to tap their finger in such a way that the rate could be measured, and then randomly assign people to take either the stimulant, and let's suppose participants were randomly assigned to take a stimulant, so either the caffeine pill, the theobromine pill, or a placebo, wait 2 hours, and then measure the rate of finger tapping. So if this were an independent groups design and each person was only doing one of the three treatments, then we wouldn't be able to control for those individual differences, right? Maybe some people are just naturally better at tapping than others. So instead of an independent groups design, we're going to use a randomized block design, and each participant here is their own block. So instead of thinking of this as 12 independent observations, each participant is their own block. And instead of trying caffeine, theobromine, or a placebo, we're actually going to have all of our participants do all three. So each participant tries all three treatments. Each participant tries all three, and the order is randomized. So that's important because otherwise we might have order effects to worry about. Maybe people get better with practice or something like that. So we want to do this in a random order. So first let's think about whether participant appears to be an effective blocking variable. In other words, does participant explain some of the variation in the tapping rates? And in this case it does. So if we look at the outcomes here arranged by participant, participant does explain some of the variation in tapping rates. Some of the variation is explained by person-to-person variability. There's sort of two ways to tell here. One is that we do have different means across the participants. So it seems like if we look at the different participants, some of them are just better at this tapping task than others, sort of regardless of the stimulant or across all three treatments. If we look at the means, we can see that participant 4 in particular tends to be much faster than the others. Participant 1 is the slowest on average. So there do seem to be some individual differences. Also, we can look at the amount of unexplained variability. We can look at the spread. So the standard deviations within the blocks, if we look within a person, are lower than the overall standard deviation. So basically, if you were using a participant to do some predictions for how fast people would tap, you would have less unexplained variability than if you were just using the overall mean as a prediction. So some people are better at tapping than others, and we want to be able to control for that. But we can't just do a difference like we've done earlier, because we have 3 different treatments that we're considering: placebo, caffeine, and theobromine, and we want to compare all 3, so we can't just subtract them. So what we're going to do is we're going to take blocks into account as part of a two-way ANOVA. So we're going to do a two-way ANOVA that includes both treatment, the 3 different types of stimulant, and the blocks, the participants. So the table on the left is a one-way ANOVA. So this is just looking at the 3 different stimulants before adjusting for blocks. So if you basically just ignored the blocks altogether and just analyzed this as a one-way ANOVA, this is the table that you would get. That's incorrect, by the way, but useful for comparison. And then this two-way ANOVA on the right, this is what you would get after adjusting for blocks. So notice that there's an additional row here. So besides the treatment, which is the stimulant, we also have a row for blocks, which is our participants. So before we discuss it, I kind of want to give you a second just to look over the table yourself. So pause the video and compare these two tables. Pay attention to what's the same and what's different. So hopefully you noticed that regardless of which table you looked at, you had the same SS total. So the total amount of variability is the same no matter how you analyze the data, and you had the same SS treatments. So the differences between the stimulants are the same, whether you account for the blocks or not. One thing that's changed is the SS error. So specifically, we've sort of split up the SS error if we compare the two tables. So before adjusting for blocks, SS error was 5,810. And if we look at it after adjusting for blocks, the error is much smaller than before. But you may notice that blocks and error together add up to the old SS error. So we've got 5,478 plus 332, and that adds up to 5,810, which was our SS error before adjusting for blocks. So basically what used to be called SS error is now broken up. Some of it has been explained. So this larger part of it has been explained by the blocks. So this is explained by the fact that some people just tap faster than others on average, regardless of their treatment. And then we have this other bit that is still unexplained. And so that's going to be SS error even after adjusting for the blocks. So let's see how to calculate the F statistic here. So the F statistic is always going to be the mean square. So like we're interested in the difference in the stimulants. So we're going to do the mean square for the treatments divided by the mean square for the error. And we've got 436 here is the mean square. So notice this is the sum of squares divided by the degrees of freedom. We have 2 degrees of freedom because there were 3 different treatments. 3 minus 1 gives us 2 degrees of freedom. And that mean square is the same whether you're talking about before or after you adjust for blocks. Then we're going to divide by the mean square for error, which is again the sum of squares divided by the degrees of freedom. And this is 55.33 after adjusting for blocks. And that's where we get our F statistic of 7.88. And to get that p-value, you would use an F distribution. And we would use the one with 2 degrees of freedom for the numerator, because that's MS treatments. And then 6 degrees of freedom for the denominator, that's MS error. And that's how we would get our p-value. So the p-value is fairly small here, 0.0210. So we've got a p-value that's fairly small, smaller than 0.05, which is a common cutoff. So we would say that this is strong evidence. And we're trying to look for a difference among the 3 treatments. So just like any other F test, we can't say which of them are different yet. This would just be strong evidence that at least one treatment is different from the others. So let's compare that to the strength of evidence before we adjusted for blocks. Notice that the F statistic is much smaller, and that's because the denominator, the mean square for error, is much larger there. So we've got a smaller F statistic that ends up giving us a much larger p-value, and so we have really weak evidence there of a difference. So basically we didn't have enough power to detect the difference between the treatments until we controlled for all of that person-to-person variability.